Hi. So now I wanted to discuss something that we've already seen before when we started talking about the Navier-Stokes equation. We used this very diagram to flow of a viscous fluid through a pipe, and we remarked that the velocity, because it's a viscous fluid, the velocity would go to 0 right at the surfaces of the pipe, but the velocity would have its maximum value at the very center, and so we guessed that the profile of the velocity would look like this. Okay. Now turns out that there's a way of deriving this, deriving the exact shape of the flow without too much trouble, and in particular this problem is called that of Poiseuille flow. Let me see if I can get the spelling correctly. Yeah. Okay. So the equation here to consider is the Navier-Stokes equation. Since it's a horizontal pipe, we don't have to worry about gravity, as in, and they're both at the same level, and so the only terms left are plus gradient of pressure. So the fluid is flowing only under the influence of pressure, and so okay. So this is the Navier-Stokes equation. Steady state, which is why you guessed it, which means the partial time derivative goes to 0. Yeah. The other thing is let's just say no body forces. In other words, the gravity terms are not important. So that's what this equation describes. Let us say that the velocity here is described by draw this again. Okay, this would be the x-axis and this would be the y-axis. So the u, and there's a gradient of Vx, there's a gradient of Ux along y, which means that the u is very simple. It becomes u as a function of y, 0, 0. So there's only a ux, and this is the ux, and that's a function of y, which means that obviously, right, which is why viscosity is important. There's a shear here, right, but this is all there is, which means that in this equation only this term and that term are important. The rest of the terms, they all fall away. Okay. So the way to write it is, it splits up into, the Navier-Stokes equation basically splits up into dp dx is equal to, right, and right, this is how it splits it, this equation just splits up. Okay. Now you see how remarkably simple this already is beginning to look. In particular, we focus only on this, nothing else, just on this. Now as far as finding out the y variation of u is concerned, this is as good as a constant, right? Think about this. This is so the other thing to keep in mind is that these plates are infinite in the direction perpendicular to the screen, and also infinite in the x direction. Okay, so that's another thing to keep in mind. So as far as this equation is concerned, the d square u dy squared, this is a constant. This is a dp dx. As far as the y variation is concerned, this one is a constant, right? So really, what you're saying is that mu equals some constant k. Okay, this can immediately be integrated. You take du dy is k times y, and u would be something like ky squared. In particular, the solution would be, and so this is a very simple equation to integrate, and in particular the solution would be something like equal to ay plus b plus y squared over 2 this k, or where this k is really, this is really a, okay, it's a pressure gradient in the x direction. So this is a plus here. I beg your pardon for my handwriting. So really, if you look at this, this is the equation of a parabola, and you apply the correct boundary conditions and it looks like a parabola. The boundary conditions would be that the velocity goes to 0 here and here, and so depending upon where you take the origin, if you take the origin here or if you take the origin at the center of the pipe, you can even get rid of this ay term, and it looks just like, you know, a y squared over 2, okay, and that's exactly the equation of a parabola. So this confirms our intuition, you know, that we started out with. On this slide we said, you know, a viscous fluid would be something, it sticks to the boundaries, and you would expect the velocity to be maximum at the towards the middle, and that's exactly what this looks like. So this is the solution to what's called a Poiseuille flow. This would be in cylindrical, I mean in rectangular coordinates. If you specialize to a cylindrical pipe, right, a cylindrical pipe, also infinite in the x direction, and so it would be something like this. So this would be the r coordinate, in which case, and this would be the z coordinate. You're just making small changes in notation. The Navier-Stokes equation now, this equation, if you write this down in cylindrical coordinates, it simply turns out to be mu over r. I'm doing nothing but writing down the relevant terms of the Navier-Stokes equation in cylindrical coordinates. Okay, and again this is a constant. As far as the r variations is concerned, this term is a constant. So you can see that you expand this out and you will have a first derivative in u and a second derivative in u, and you apply the appropriate boundary conditions, and turns out a radial. So again it's a parabola. You will have the full solution actually will be something like so this would be a parabolic kind of thing in R. As such, you would have a logarithmic term, but if you apply the boundary conditions correctly, you will find that A has to become 0, and the particular solution becomes this. The radius of the pipe is A. Okay. So it turns out that the particular solution is squared over 4 mu dp. This is the solution we are after, mind the 2 here. So this is a solution for, again, and this also, the profile of this also looks like this, okay, with a maximum at the center and 0 at the ends. So this is a solution for flow of a viscous fluid inside a cylindrical pipe. So this is, I figured out, introduce these things by way of simple examples of solutions to the Navier-Stokes equation. Okay, and I have not sketched out every single step. I urge you, especially for instance, applying the boundary conditions correctly so that you figure that A and B are both equal to 0, and those, well, B is not equal to 0. That's how you get the A squared, right? So I urge you to do those steps So it's useful to demonstrate how simple solutions to the Navier-Stokes equation, not merely talk about the equation, right. So it's in that spirit that I said this. Now, I figured I would say something a little off the mainstream of what we've been talking about, but you see, we've been talking about viscosity a lot, and so mu, which is the viscosity coefficient, which has units of, right, is an example of what's called a transport coefficient. What does it describe? It describes the transport of momentum. And this is simply taken to be a property of the fluid. This is a particular number for a particular fluid, just like thermal conductivity or something else, right. Now, we talked about how transport coefficients, well, how bulk properties like density or velocity or some things like this are derived from microscopics towards the very beginning of the course. Let us, I figured we would revisit this thing about a viscosity coefficient, and in particular show how this this corresponds to transport of momentum, in particular momentum flux between layers, and how a viscosity coefficient is derived using the concept of a mean free path, using microscopics a little bit, right. It's quite simple. So let us consider a situation where you have a two-dimensional flow, and same thing as before. You have z like this and y like this. So you have a situation where u is equal to u as a function of y in the z direction. Okay. So the shear stress from which viscosity is derived, remember, is nothing but the net flux of z directed momentum in the y direction. In other words, if you have a layer here and here, remember our analogy of suppose this was a viscous fluid, and you had a larger velocity here and a smaller velocity here. Viscosity, remember, was all about little rubber bands joining these two layers. And what do these little rubber bands do? They refuse to let smooth sliding happen. Let me draw these rubber bands a little better. And so what do the rubber bands really do? They carry the fact that there are particles, and these would be separated by approximately one mean free path. Okay, in a microscopic sense. And what they would do, so molecules or atoms as the case might be, from this layer would go from here to there and carry the information that right here there's this amount of flux of z momentum, and they would and when they hit this layer, which is spaced one mean free path apart, they carry that information that there's this flux of z momentum, and they tell this layer about that information. And when the collision happens, this layer, as a result of the collision, it slows down. And so that is sort of where the rubber band analogy comes in. Okay. In particular, you can write down something like a unidirectional particle, say the expression for a unidirectional, crossing the y equals 0 plane. This is something like rho this is the unidirectional particle flux, well, mass flux per particle, or I should say mass flux. If I was strictly talking about particle flux, this would be n VRMS. If I'm talking about mass flux, it's really rho VRMS, right? And the other thing to remember here is that the magnitude of the average z momentum carried by particles within a mean free path lambda, right? And so this is the other important thing. So the average z momentum carried by particles within one mean free path now is something like du dy times lambda. Okay. So you multiply that with this, right? So you have this times rho times VRMS. Okay. And because of the fact that you have particles going on both sides of the plane, you have a factor 2. Okay. Now remember, I said that the shear stress is essentially the net flux of z momentum in the y direction. So that is this. That completes this. The net flux of z momentum, this entire thing is the net flux of z momentum in the y direction. And we arrived at this from a particle kind of picture. Yeah, the average z momentum carried by particles within one mean free path is this, and this is the net particle flux. And the shear stress by definition is equal to, this is how the mu is derived from the microscopics, and this is equal to du dy. So this is how you derive mu from the microscopics, from things like the RMS velocity of the particles that constitute the fluid. Okay. Now remember, in order to have a meaningful definition of a fluid, you should have many mean free paths in any representative macroscopic length scale. So all that is very much there, but I figured this is how I would give you an illustration of how a transport coefficient such as a viscosity coefficient is derived from the microscopics, right? So in some sense, yeah, okay, so this is a macroscopic quantity, the du dy, but the rest of it are all sort of microscopics, and everything really depends upon this mean free path. Okay, if the mean free path is large, the viscosity would be large, and vice versa. However, the mean free there are funny situations such as collisionless fluids or collisionless plasmas, where the mean free path is actually the regular collisional mean free path for regular collisions between particles is actually much larger than any meaningful macroscopic length scale. And in such situations, you cannot apply this simple-minded expression, and you would have to find an effective mean free path that is not simply the collisional mean free path. Let me write this down. Since I'm saying this word over and over again, I should write this: mean free. And you would have to find a more meaningful mean free path that is not simply the collisional mean free path. But that's for collisionless fluids, and that's a bit of a special situation. I just thought I would show how a macroscopic transport coefficient, which is regarded as a property of the fluid, is derived from the microscopics, before going on to talk about the other aspects of the course and transitioning again to fluids, and not from a microscopic point of view, but just the macroscopic fluids, where we simply talk in terms of transport coefficients. So that's it for now. Thank you.